This video is going to go over the first part of 1-3 piecewise defined functions. First, we have our essential question. How do you model a situation in which a function behaves differently over different parts of its domain? So instead of graphing lines across an entire coordinate plane, today we're going to be looking at graphing only for certain x values. And you'll see what I mean whenever we get to the first example. So we have a couple of definitions here. Scroll so you can see all of that. First, you have a piecewise defined function, which is a function that has different rules for different parts of its domain. So, as I said, rather than a line existing for all of the x values, it's only going to exist for maybe all the x's that are less than 2, or all the x's that are greater than 5. So it's not going to have free reign to just go across the entire graph. We also have step functions. Those are a specific kind of piecewise defined function. That's where every input is going to be within some interval is going to be the same output value. Step functions are going to resemble staircase when graphed. So this is going to be like a series of horizontal lines as you're going up. Okay, so this brings us to example 1. And I'm just going to go through and calibrate this real quick because it doesn't seem like the board is cooperating here this morning. Whenever you are graphing a function like this, a piecewise defined function, you're always going to have some type of value here on the right-hand side that's going to be known as your boundary. Your boundary is where one function is going to stop and another function is going to start. So for this question, our boundary here is at x equals -4. So I want to go to -4 in the x-axis, and I'm actually going to draw in a dotted line there. So I have my dotted line there at x equals -4. That means that one function is going to exist on the left of -4, and one function is going to exist on the right of -4. So you want to go and look at the original problem and see where the x values would be on the left. Those would be the -5, -6, so those are the things that are less. And the ones that are on the right are going to be greater. That's going to be -3, -2, -1. So my top piece here has the less than sign. So this one is going to be on the left. On the bottom, I have a greater than sign. So that one is going to be on the right. The other thing you have to consider, and I'm actually going to write that right in a different color so that we can keep those separate whenever we're graphing. Whenever I do this graphing, I will be using different colors. Again, that's going to help you distinguish which piece we're talking about. The other thing you need to consider is whether you have open or closed dots on the boundary. Now, if you are not on the boundary line, all of your dots are going to be closed. It's only on this dotted boundary line that we drew that you could potentially have, well, you most likely will have at least one of the dots. So if you look at the top piece, I have x is less than -4. There's no line under that inequality. That means that that dot is going to be closed. I know that kind of looks like ghost, but that says closed there. On those, or I'm sorry, that's going to be an open dot, not a closed dot. See, I'm really confusing myself here. So if there is no line under the inequality, that dot is going to be open. If there is a line under the inequality, it is going to be closed, like the bottom piece. Now you actually want to look at the function. This g of x goes to both of these pieces. So you have g of x equals -1 and g of x equals 5. So your function is actually -1. Well, -1 is a horizontal piece. So it is a horizontal. You're basically graphing the line y equals -1. It's going to have an open dot on the boundary. So I want to go to the boundary and I want to go down to -1. And it exists to the left of that boundary So that line would be going out to the left. For the 5, again, that's another horizontal line. That is the line y equals 5. That is going to start with a closed dot. So I'm going to go again on the boundary up to 5, draw my closed dot, and then I'm going off to the right, because that one exists to the right. And that's a piecewise function. This would be considered a step function because the pieces are horizontal. And then the next example, you'll see how we graph whenever we have something that is diagonal, when you have an x thrown in there instead of just a number. Okay, so this is example 2. Again, I have 2 different parts to my function. If we look at the top part, so I have -2. I have a line under the inequality. I'm going to have my boundary at 4. So I'm going to go ahead and draw in that dotted boundary there at 4 while I'm thinking about it. So y equals -2 is horizontal, and it is going to be a closed dot on the boundary. So I'm going to go on the boundary, go down to -2, closed dot. This inequality symbol is less than, so that is going to exist to the left of the boundary. I'm going to draw that in. Now the other piece, the x, that is the equation y equals x. That is diagonal, and it is going to be open on the boundary. But now to figure out what values you're actually going to be graphing, we are going to plug in x's that exist within this boundary. You always want to plug in the boundary value. So we are going to plug in 4. So when I say plug in 4, you're going to plug in 4 for x. So I'm now going to have the equation y equals 4. Well, there's no math to do there. There's nothing to simplify. So if you plug in 4 for x, you get back 4 for y. That gives me the ordered pair for 4. That is on the boundary, so it is going to be open. So 4, up 4, and I put a dot. There's this nice open dot there. Now we need to pick one other x value that is within that boundary. So I need another x value that is greater than 4. You could use 5, you could use 6, you could use 7. I'm just going to go ahead and plug in 5 for x. That now gives us the equation y equals 5. So my ordered pair is going to be 5, 5. Because 5, 5 is not on the boundary line, it's automatically closed. The only time you have to worry about open is whenever you are on the boundary line. Otherwise, everything is closed. So 5, 5 is right here, and I'm going to draw through that, and there's my graph. So this one actually is going to exist to the right of the boundary in my ordered pairs. This can be confusing the first time that you see it. This is definitely something you're going to have to practice for it to make sense. I will continue using colors when we go through this, and you'll see in the next one we actually have 3 pieces instead of 2. Again, I'm going to use a different color for every one, and we're actually going to have 2 boundaries instead of 1 boundary. Okay, so this is example 3. This is actually the last one that we're going to look at in this particular video. We got lots of that, well, 2 different boundaries going on here. So you see I have the -2, then the middle piece picks up with the -2 and continues with the 4, and then the last piece is also going to use the 4. So -2 and 4 are the 2 values that appear in the boundaries. That's where I'm going to be putting my dotted lines. And there's my -2. there's my a top piece. This is diagonal. It is going to be closed. So this is the equation, y equals negative x minus 1. It is diagonal. And it is also going to be a closed dot. And you'll see by my ordered pairs, because it's less than negative 2, it's actually going to exist on the left of the boundary. So I have to plug in two values. I'm going to plug in, you have to use the boundary of negative 2. So that gives me y equals negative 2 minus 1. Well, double negative 2 is going to be positive 2 minus 1 is 1. So this is the ordered pair negative 2, 1. So negative 2, 1 is right there, and it is a closed dot. So I need another value that is within that boundary. Well, that boundary is all the x's that are less than or equal to negative 2. So you could use negative 3. You could use negative 4. You could use negative 5. I'm just going to use negative 3 because that's one of the closer values. So I have y equals negative 3 minus 1, which is going to give us 2. So that's the ordered pair negative 3, 2. So negative 3, 2 is right there. To connect these dots, I'm going to start on the boundary and draw through the other dot. So start on the boundary and draw through the other dot. Notice that I'm not crossing over that boundary. I'm on the boundary, but I'm not crossing through it. The middle piece also has an X in it, so that is another diagonal line. Okay. So this again is diagonal. The middle piece is unique because it has one inequality that has no line under it, and then another inequality that does have a line under it. So this one is going to go from open to closed. So you're going to start out on the negative 2 boundary, you're going to have an open dot. On the 4 boundary, we're going to have a closed dot. Because this particular function, this 2x minus 2, is bound between negative 2 and 4 for the x's, those are the two values that we're going to plug in. So plug in negative 2, we get y equals 2 times negative 2 minus 2. So 2 times negative 2 is negative 4, minus 2 is negative 6. So that is negative 2, negative 6. That is an open dot. Negative 2, negative 6 is an open dot. You should never have two closed dots above each other. So that is one way that you can check yourself whenever you're going through these questions. It shouldn't be closed dot, closed dot. You could potentially have two open dots above each other, but you can't have two closed dots. It wouldn't be a function then. And then I'm going to plug in my other boundary of 4. So y equals 2 times 4 minus 2, which is 6. That's going to be the ordered pair 4, 6. And that one is closed. 4, 6 is going to be a closed dot because this is dot to dot, boundary to boundary. I'm going to connect those. Got a nice line. And the last piece, new color here, purple. The last piece is horizontal. So I don't really need to worry about values. I am going to the right of my boundary. And this piece is also going to start with an open dot. But you notice, if I'm at a height of 6 on the boundary, that puts me right on top of that closed green dot. So even though I'm drawing an open purple dot over top of that closed green dot, it still counts as a closed dot. So you're not actually going to see both the open and the closed. You're only going to see the fact that there's a closed dot there. And then this one is drawing off to the right. So this one is a little tougher. We aren't going to do too many of the 3 equation ones. I really want to focus on the 2 equation ones and make sure that we get comfortable with graphing those types of questions. We may throw some of these in here periodically though. The important thing is to make sure that you are able to graph a line that is in slope-intercept form. I know we're just plugging in points, but like this y equals negative x minus 1, y equals 2x minus 2, those are mx plus b equations. And for example, if you look at this green equation, it has a slope of 2 and a y-intercept of negative 2, and you can see the green line does cross at negative 2, and it's up 2 and over 1, which would be a slope of 2. For the blue equation, even though it doesn't actually cross the y-axis in the piece that we have, it does have a slope of down 1 over 1, and if I were to keep counting it, it would eventually cross. You can see if I extend that, it would eventually cross at negative 1. So all of those previous rules still apply for graphing. Please go back, watch this video if there was anything that you didn't understand. Watch it as many times as you need. And if you still have questions, please reach out.